Good morning and welcome to Theater of the Cosmos Coffee. This is where I normally will take the archive.org AstroPH listings from the last week and kind of on the fly go through them and discuss what they're about and maybe the implications to origins and creationism. But here, this being the inaugural one, I decided to just pick a topic and we'll go through this particular paper. So about a month ago, September 18th, this paper came out in Nature that showed the largest black hole uh, jets known so far. And it's quite an interesting topic, especially as it relates to origins and it's making astronomers rethink some of the Big Bang model and the galaxy evolution, black hole evolution, all of those things, which is going to be exciting to see. So here I've got the abstract for the original paper up on the website here. You can see the authors, and first off, what is this jet? Well, it's a bunch of high energy particles and a magnetic field that driving them out into the intergalactic medium. So the space between galaxies, and this has an effect because it's far-reaching. So for the past 50 years, up to this point, the largest jets were about 4.5 to 50 or 4.5 to 5 megaparsecs, which reaches out to 20 to 30% of cosmic void radius. But this one spans 7 megaparsecs, which takes it out two-thirds of the way, almost all the way across the cosmic void. So what is the cosmic void, cosmic web? It's the large scale structure in our universe. And let's see, NASA here has a nice little animation of it. Basically, if you think of the universe as a big sponge, and the material of the sponge are galaxies, and um, the voids are those holes in the sponge. So that's what we're talking about. So here you can kind of see we're flying through. And you see there's strands of galaxies here and there, but these big gaps between them you can especially see if you look off in the distance in this video. So that's the fact that this one reaches two-thirds of the way, or almost basically across uh, the cosmic void, is that now there's really no place in the universe that doesn't interact with other parts of the universe, which is interesting no matter what your perspective on cosmology is. I think the last couple sentences here uh, are what make this story interesting to me. So, this system demonstrates that jets can avoid destruction by magnetohydrodynamical instabilities over cosmological distances, and how jets can retain such long lived coherence is unknown at present. Basically, what this is saying is astronomers don't understand how or why these jets have gotten so big, how they've lasted so long. As we'll see, it requires a very stable system to last over that long period of time if you're taking a Big Bang cosmology approach. So this is the main paper. For I think a really good summary, phys.org, an article here. So you can see the artist rendition of what they think an artist rendition of what these jets look like. So you've got the cosmic void here and the strands of galaxies. Here's the galaxy that has the supermassive black holes in it, the cosmic jets flowing off of that. Again, that's just an artistic rendition, but it's a good illustration. So just to go through this article really quick, to give you an idea how big these jets are, if you stacked 140 of our Milky Way galaxies side to side. That's how long these jets are. So 23 million light years. So if you can even fathom that size. It's been nicknamed Porphyrion after the largest of Greek giants. Another uh, statement to kind of wrap your brain around how major this is. The total power output of these jets is equivalent to trillions of suns. And that's even more amazing when you think that it's in the radio spectrum, which is the lowest energy part of the spectrum. So because these are so high energy and they reach so far, it has the implication that these kind of jets actually influence the formation of galaxies, the large scale structure of the universe. All of those things are going to be affected by these jets, especially if you're using a Big Bang model and they're lasting over such a long period of time. All right, so a little bit of background on the research project that found these. They're using the LOFAR radio telescope. LOFAR here is mainly in the Netherlands, but if this page will load. So here's a picture. So it's mainly in the Netherlands, but it is actually all the way across Europe. Uh, a radio telescope array. So you have these radio telescopes spread out because the more spread out you have them, uh, the more detail you can see in the image. So this is a LOFAR telescope, and basically the project that this came out of has found more than 10,000 of these large radio jets, which is totally unexpected. In fact, this particular uh, research project started back in 2018 here to look at that cosmic web, not to look at these black hole jets, and they happened to find it, which I think, to me, this makes uh, a much more interesting story. Those those research findings that you don't expect, because that's where we find new things because we didn't expect it. Uh, Isaac Asimov, I think, has a saying that the most exciting phrase in science is not "Eureka, I found it," but that's interesting. So it's in those unexpected findings that we learn the most. So how did they do this? Well, they set up a way to systematically search for hidden jets once they started finding them, um, using machine learning, uh, looking at the images by eye, but also using what's called citizen scientists. So I think Galaxy Zoo was the website they used for this, where anyone can actually go in and label things. And the original paper before the Nature paper is here was published in Astronomy and Astrophysics, um, basically outlining the way they used machine learning, that version of AI, to to accelerate the ability to catalog system. Their aim was here to automate creation of radio optical catalogs. So that's how you find thousands of examples. Uh, so the conclusion here, I think, is interesting. So we present a state-of-the-art machine learning accelerated pipeline for fighting giants, and it says because they're complicated objects, so you need a strong machine learning model to find them. But then it says our data analysis suggests that giants are more common than previously thought. More work is needed to make GRG low VFF estimates. Basically, they're saying these large jets, these large radio jets from black holes, are more prevalent than expected, and so that challenges black hole evolution. That challenges galactic evolution, large scale evolution. It really, at the core, challenges the Big Bang model. Uh, so the last piece here, going back to phys.org, um, that I found interesting was this paragraph here. This Porphyrion came from a radiative mode black hole. So a radiative mode black hole is not one that's supposed to be giving most of its energy off in a jet. So there's two categories here. There's the radiative mode black hole and the jet mode black hole. Excuse me. The radiative mode black hole is supposed to be more common in the distant universe and, and not so common nearby, which from a Big Bang perspective means it's more common in the younger universe. um, they're supposed to emit their energy primarily in the form of radiation, not jets. Typically found in galaxies that are bluer and more towards the spiral end of the spectrum of galaxies rather than elliptical and redder galaxies. Again, that's supposed to imply it's a younger setting. They're supposed to accrete matter at a higher rate, so lots of matter falling into the black holes, and they're often associated with quasars or highly luminous active galactic nuclei. Whereas jet mode black holes, so ones that they emit most of their energy in jets, are supposed to be more nearby. They're usually found, like I said, in massive elliptical redder galaxies. Again, it's supposed to be older. They accrete matter at a lower rate, and they're associated more with radio galaxies than quasars. So, but the fact that this Porphyron was in a radiative mode black hole kind of messes with that model there. So the last piece I want to point out from this article is this quote by one of the authors. This was Hardcastle. This is Mark Hardcastle. Um, says my interpretation is that we need an unusually long-lived and stable accretion event around the central supermassive black hole to allow it to be active for so long, about 1 billion years, and to ensure that the jets keep pointing in the same direction over all of that time. What we're learning from a large number of giants is that this must be a relatively common occurrence. So that first sentence makes it sound very difficult to achieve. It has to be a stable system for a long period of time, which is not what astronomers would think would be the most common thing. But what they're finding is they're very common. So again, this seems to go against typical thinking in astronomy. And so now we get to kind of my perspective and what this means for the future of astronomy and really to be more specific for creationist astronomy. I'm going to show you the actual picture. Uh, you're gonna, okay, well, I'm not going to put my email in there. But for creationist astronomy, I think this is really interesting because this is a system that's supposed to be short-lived, but if we take the Big Bang model, it has to be long-lived to make these large jets. And so maybe if we have a different model of the universe where the universe is much younger, then you don't have to worry about that stability issue. And these jets might make more sense. But again, I'm I'm shooting from the hip here. I haven't thought deeply on this uh, to actually build a theory. But I find it interesting because I think this also lines up with a lot of the JWST findings, where the further out astronomers look in the universe, the more, not the more mature, but they find galaxies that are more mature than expected from a standard galactic evolution framework. And so putting these together, I think is really interesting from a creationist perspective because these don't go with the Big Bang, but they might go with a creationist model. Whether, well, I won't go down that rabbit hole, but uh, it'll be interesting to see where these go, and I'd really like to see some creationist astronomers tackle this and maybe give some explanations for it. So thank you for joining me. Hopefully next time we'll have some Astro PH papers to go through, and I look forward to taking this journey with you. Thank you. And until next time, keep looking up.